All right, welcome to this explainer. Today we're diving into the science of food texture. I mean, think about it. How do we turn the crunch of a chip or the firmness of an apple into actual hard data? That's what this is all about, the instruments and the science that let us measure the feel of our food.
You know this feeling, right? You reach into a bag of chips, expecting that perfect, satisfying crunch, and instead you get something kind of soggy and sad. We all know that difference instinctively, but for a food scientist, the real question is, how do you put a number on that difference? That's the problem we're trying to solve here.
Okay, so here's our game plan. First, we'll talk about why texture matters so much. Then, we'll look at how humans stack up against machines in measuring it. We'll cover the basic language you need to know, walk through 4 really important tests, and finish up by looking at where the science is headed. Let's get into it.
So first things first, why do we even need to measure texture with instruments? Well, it's about a lot more than just whether you or I like something. We're talking about quality, safety, and ultimately whether a product succeeds or fails in the market.
Texture is absolutely not just some minor detail. It's a huge deal. It's often the main reason we decide to buy something again. Think about it. It also dictates how food holds up during processing and packaging. It's a massive part of quality assurance, a critical point in systems like HACCP. And get this, it even changes how we perceive other things like flavor and juiciness. A crisp apple just seems juicier, right?
Okay, so if we want to evaluate texture, how do we actually do it? Well, we've basically got 2 tools in our toolbox, human beings and machines. And as you'll see, each one brings something really different and really important to the table. And this is where it gets really interesting. On one hand, you've got trained human tasters. They are amazing at picking up on tiny differences like, this cracker is just a little bit crispier than the last one. But they're subjective. On the other hand, you have instruments that give you the cold, hard facts, the objective numbers. The real magic happens when you can get those 2 to line up, when you can correlate the machine's data with what people are actually experiencing.
All right, before we dive into the actual tests, we need to make sure we're all speaking the same language. These instruments are based on some fundamental concepts from materials science, so let's quickly build our vocabulary so the rest of this makes perfect sense.
First up is stress. You'll see it written as the Greek letter sigma. Now, this isn't just about force. It's about how concentrated that force is. For example, imagine pushing on a tomato with your whole palm versus poking it with your finger. Same force maybe, but the finger creates way more stress because the area is so much smaller. That's a crucial difference.
Okay, next up we have strain, which is epsilon. So if stress is the force we're applying, strain is how much the food actually changes shape in response. It's a relative change. If you squish a 10-centimeter tall piece of tofu down by 1 centimeter, the strain is 1/10, or 0.1. It's just a ratio, so no units to worry about here.
Now let's put those 2 together. The ratio of stress to strain gives us something called the modulus of elasticity. You can just think of it as a measure of stiffness. A food with a high modulus, like a raw carrot, is really stiff. You have to apply a lot of stress to get even a tiny bit of strain or deformation. A low modulus food, like a gummy bear, is the opposite. So, all of this comes together visually in a stress-strain curve. This graph literally tells the story of what happens to a food as you apply force. And for foods, it gets really interesting. You often see this specific point, the bioyield point. That's the exact moment the structure starts to fail. Think of it as the point of the first crunch. It's a really, really important textural event to capture.
Okay, theory's over. Let's head into the lab, so to speak, and see how we put all this into practice with 4 of the most fundamental tests that food scientists use every single day.
First on the list is uniaxial compression. And really, it's just a fancy way of saying we're going to squish something in a very, very controlled way. You take your sample, maybe a little cylinder of cheese or a piece of fruit, place it between 2 plates, and just compress it. And why do we do this? Well, the machine measures the force we apply and exactly how much the sample deforms. And with those 2 numbers, we can calculate our stress and our strain. And what do you get when you divide stress by strain? You get that modulus of elasticity we just talked about. Boom! We now have a number for firmness. All right, so if compression is squishing, the opposite has to be pulling, right? That's our second test, uniaxial tension. Here, instead of pushing, we're pulling a sample apart. This is super useful for looking at things like, say, how well a meatball holds together. But, and this is a big but, tension tests are actually really tricky to do with a lot of foods. Just think about it. How in the world do you grip something soft and wet, like a piece of fish,
hard enough to pull it without just shredding it right there in the clamps. It's a real headache and a big challenge. Okay, on to our third method, shear. Now this one is all about trying to mimic what your teeth do. We're talking about cutting, tearing, and grinding. So shear tests are what we use when we want to put a number on concepts like tenderness or toughness. And just like with any job, you need the right tool. For something uniform like a hot dog or a carrot, you might use a Warner-Brаттler device, which is basically a single blade that slices through it. But what about a handful of peas or some ground meat? For that, you'd need something like a Kramer shear press, which has a bunch of blades and measures the average force to chew through the whole sample.
And that brings us to our fourth and final test, bending. This is usually done with what's called a three-point bend test. It's perfect for anything that's supposed to be rigid or brittle. Think crackers, cookies, that kind of thing. We're measuring stiffness and ultimately what it takes to make it snap.
And you can use this test for a surprising range of things. Seriously, you could be measuring the brittleness of an animal bone to check its nutrition, or the force it takes to snap a pretzel. You can even use it to put a number on that satisfying pop you get when you bite into a really good sausage. It's super versatile.
So, okay, we've got compression, tension, shear, and bending. It sounds like we have this all figured out, right? We have a test for everything. Well, not so fast. The reality, as always, is a little more complicated.
The truth is, and this is a key takeaway from the source material, measuring food texture is not an exact science. Not yet, anyway. Each of these tests gives us a valuable piece of the puzzle. But think about how complex chewing is. No single machine can perfectly copy everything that happens in your mouth. So the search for better instruments, better techniques, that search is always on. So why does all this matter? Because getting a handle on these measurements is absolutely fundamental if you're in food science. This objective data is the key. It's what lets companies create new products, guarantee quality, and make sure that bag of chips you buy today has the exact same crunch as the one you buy next year. It's all about consistency and innovation. And that leaves us with one last big question to chew on, so to speak. We're creating foods that are completely new. Plant-based steaks, 3D printed snacks, you name it. Their textures are going to be unlike anything we've measured before. So the challenge for you, the next generation of food scientists and engineers, is this. How are we going to measure the texture of foods that don't even exist yet?